So here's a problem. We're going on a walk from the bottom left corner to the top right corner of a grid along the grid lines. If we're not allowed to visit any intersection more than once, which grid shape would have more ways for us to take this walk? A narrow and long grid or a square grid of the same size? Take a second to decide on an intuitive answer for yourself before we take a closer look, because the result was quite a surprise for me when I did my own exploration on this problem. My name is Sturdos. I'm on a mission to collect interesting math problems for school-aged children, and I'd like to take you along. Let's start with the simplest case of just one square. To go from the bottom left corner to the top right corner, we can go either right and up or up and right, just these two ways. We can't take detours anywhere because there's no space. With two squares in a row, there are three shortest paths from the bottom left corner to the top right, but there's also this one that takes a bit of a detour, so four in total. With three squares in a row, there are four of those shortest paths, but there are also more ways to take a detour. Four of those to be exact, for a total of 8 ways to get from the bottom left corner to the top right. If we keep going, we can spot some patterns. The number of shortest paths increases by 1 with each square we add, while the total number of walks doubles each time. If we can figure out why this happens, we can show that these patterns will continue. Drawing out the shortest paths for each of these grids makes it easy to notice the reason. To get from the bottom left corner to the top right corner, somewhere along the path we'd have to go up just once, and all other steps are to the right. Since the number of vertical grid lines to choose from is always one more than the number of squares, and once we choose that vertical line, there's only one shortest path we can draw. The number of these shortest paths must also be one more than the number of squares. So why does the total number of walks double each time? If you're familiar with counting principles, where we multiply the number of options with each independent choice, which we've gone over in a bit more detail in the connected lights video, you might have noticed it. The fact that it doubles each time seems to suggest that we're introducing a new independent choice with 2 options with each square we add. Let's try to make sense of this line of thought. If we imagine cutting the grid as we walk along its lines, each square is either above the cut or below the cut. That's 2 choices for each square. For any combination of squares above and squares below that we decide to have, we can design a walk through the grid that separates them to fit the combination. Start by cutting each square on the correct side horizontally, and then connect those cuts to each other and the starting and ending points by using the vertical grid lines as needed. Each combination gets exactly 1 possible walk this way. So the number of total possible walks is just a product of all the options we have when deciding above or below for each square. Now, what happens if there are more than 1 rows of squares in the grid? With the smallest case of the 2x2 grid, we can also try to separate the squares into ones that are above the cut and ones that are below. For the first few combinations we try, we can find a unique path for each of them, which makes it look hopeful that we can count the number of walks from the bottom left corner to the top right corner just by counting the ways we can assign squares to be above or below the cut. However, we need to clear a couple of conditions to be able to do that. One is that there's no way for us to make 2 different paths from the bottom left corner to the top right corner for the same assignment of the squares to be above or below the cut. The other is that there is no assignment of the squares that's impossible to make a path for. Are these true though? If you're enjoying this problem, I made it into a book, so you can share it without giving away the solutions. Check out the link in the description below, and back to the video. Let's follow the decision-making process for which path to take for a given assignment of squares to be above or below the cut. The first decision we have to make is whether to go up or to the right at the starting point. This depends on whether the first square is assigned to be above the cut or below the cut. Only one of those choices work once we know which side the square is assigned to. From there, we follow the outline of the region of squares that are assigned to the same side until we come to another edge of the grid. Then we take on the next neighboring region and follow its outline. Repeat until we reach the endpoint on the top right corner. If the outlines of these regions are clear, there is only one path we can take for each assignment of squares. This clears the first of the two conditions for us. However, we do run into some problems with the second condition. If a region is shielded by another by being surrounded, either partially or completely, then there's no way for us to cut along the outline of the shielded region without visiting the same intersections or even the same grid lines twice. If we don't try to access it this way, we would be following along the outline of the outer region without ever touching the inner one. There are also cases where the outlines of the regions are not completely clear. When neighboring regions meet in this crisscross pattern, for example, we have a few choices on which ones to consider connected. Regardless of how we divide the regions here, this intersection has to be visited more than once to make all the cuts. So none of these are valid walks in our final count. But just for the sake of exploration, let's see in how many ways we can cut this small 2x2 example. If we think of these two as one region and separate the other two, here's one way to cut them. If we switch and consider the other two the same region, here's another way. Then there are ways where we cut straight through the intersection and cross it in the other direction later. As we mentioned earlier, none of these can make a valid path though, because the central intersection is always visited twice. In fact, whenever we have an intersection among four squares like this, there will always be similar assignments of squares that can't have valid walks. Now we have all the pieces we need to answer our initial question. In the case where the squares make narrow and long grid of one row, the number of diagonal walks is the product of the choices we have when assigning each square to be either above or below the cut. In the case where the squares make more rows, the number of diagonal walks is the product of those same choices minus the ones that can't make a valid walk, namely the cases where those squares are shielded by an outside region and the cases where four squares make a crisscross pattern at an intersection. This means the squares in a single row will always have more diagonal walks. Did you guess it right? By the way, those two special cases also generalize to irregular grids where the inner intersections don't always have four squares. The arrangements that don't result in a valid walk can still be categorized into either a region being shielded by another or a crisscross pattern at an intersection. Phew, math makes sense again. Now I wonder how counting diagonal walks work in three-dimensional grids. Let me know what you think in the comments below, and until next time, stay curious.